Good day. My name is Dr. Mary Ajide from M2E Lab, which is the Advanced Interfacial Modeling Across Energy and Matter. Thank you for the opportunity to present this work entitled A Transferable Active Learning Machine Learning Interatomic Potential Framework for Predictive Simulation of Reactive Oxide Water Interfaces. Let me start with a central challenge in computational material science. Can we simulate how reactive surfaces behave in contact with water at the scale of individual atoms and over time scales that actually matter for real chemistry? Picoseconds are simply not enough. We need nanoseconds, microseconds, and beyond. First principles method like density functional theory gives us quantum mechanical accuracy, but they are computationally expensive, typically limited to a few hundred atoms and a few picoseconds. Classical molecular dynamics is fast but lacks the quantum accuracy needed for reactive chemistry. Today, I'll describe a framework that bridges this gap. An uncertainty-driven active learning machine learning interatomic potential pipeline. We demonstrate it on the hematite-water interface, one of the most chemically complex and practically important systems in material science. But crucially, the framework is fully transferable. Everything I show you today can be adapted to other reactive interfaces in catalysis, electrochemistry, and environmental science. Let's begin with the question of why reactive oxide-water interface matters so much. Oxide-water interfaces are everywhere, from the iron minerals in soil and ocean sediments to the electrode in next-generation batteries and fuel cells to the corroding infrastructure we rely on daily. Hematite, or alpha iron 3 oxide, is particularly important. It's one of the most abundant minerals on Earth's surface, a photocatalytic material for solar water splitting, and a model system for studying charge transfer at oxide-water interfaces. Yet, despite decades of experimental and computational study, we still don't have a clear atomistic picture of how water interacts with these surfaces. How does water dissociate? How does it restructure the surface? What does that do to the electronic structure? The reason is simple. The time scales and length scales involved in these processes are inaccessible to conventional first principles methods. We need a better approach, and that's exactly what this work provides. Let me now explain why conventional ab initio molecular dynamics fall short and what we need to do in order to overcome those limitations. So let's be concrete about the problem. Ab initio molecular dynamics is incredibly powerful. It computes forces directly from quantum mechanics, capturing bond breaking and forming with no empirical input. That's exactly what we need for reactive surface chemistry. But here's the steep price. Ab initio molecular dynamics scales as the cube of the number of electrons, which severely limits the system sizes and simulation times we can access. In practice, we're talking about a few hundred atoms and a few tens of picoseconds. That's simply not enough to see water dissociation events, proton transfer chains, or hydration layer restructuring, all of which requires nanoseconds or longer, and large interfacial models. There's a gap of roughly 3 to 6 orders of magnitude between what ab initio molecular dynamics can access and what the chemistry actually requires. Closing that gap is the central motivation for this work. The question becomes, can we retain the accuracy of quantum mechanics, but at a fraction of the cost? That's exactly what machine learning interatomic potentials are designed to do. Machine learning interatomic potentials represent a genuine paradigm shift in computational material science. The core idea is elegant. We use a relatively small number of quantum mechanically accurate DFT calculations to train a machine learning model that can reproduce the DFT energy landscape. Once trained, this model predicts energies and forces at a cost comparable to a simple classical potential, but with DFT accuracy. This isn't a new idea. Neural network potentials have been around since the work of Biller and Perenello in 2007, but the key advance in our framework is how we train and validate the model. Rather than generating a fixed trainee dataset upfront, we use an adaptive, uncertainty-driven active learning strategy that systematically explores configurational space as the simulation runs. And critically, the model doesn't just predict energies and forces, it also provides a Bayesian estimate of its own uncertainty, essentially telling us when it encounters a configuration it hasn't seen before. This is what makes the active learning loop possible, and it's what keeps the framework physically reliable throughout. Let me now show you exactly how this workflow operates. This is the art of the framework, and it's worth spending a moment understanding how all the pieces connect. We begin with stage 1, building an initial set of diverse reference structures, different surface terminations, water coverages, and configurations, chosen to span the key regions of configurational space. We then now move on to stage 2, where we run DFT calculations on these structures, computing energies, forces, and stresses. This becomes our initial training data set. In stage 3, we train the machine learning force field on this data set. The model we use provides not just force predictions, but also Bayesian uncertainty estimates, essentially a confidence score for each prediction. We then now move on to stage 4, where the active learning loop begins. We run molecular dynamics using the machine learning force field, but at every step, we monitor the Bayesian uncertainty. When uncertainty is low, we trust the machine learning force field and continue propagating. When uncertainty exceeds our threshold, meaning the model has encountered an unfamiliar configuration, we pause and run a DFT calculation. In stage 5, that DFT result is added to the training set. The model is retrained and we continue. This loop runs until uncertainty stays consistently below the threshold, meaning the model has converged to cover all relevant configurational space. Stages 6 through 9 cover validation, long-timescale production, molecular dynamic, trajectory analysis, structural and dynamical analysis as well, and electronic structure interpretation. I'll discuss each of these in the following slides. For our proof of concept system, we chose hematite, alpha ion oxide in contact with liquid water. This isn't an arbitrary choice. Hematite is one of the most studied oxide surfaces in computational materials science, which means we have excellent reference data to benchmark against. But it's also genuinely challenging. The ion-oxygen covalency, the spin structure, and the complex surface termination chemistry all play heavy demands on the machine learning model. Our initial training dataset was built from diverse configurations: clean hematite slabs, partially hydrosylated surfaces, water monolayers in both molecular and dissociated forms, and fully solvated interfaces with explicit liquid water. This diversity is critical. It ensures the model encounters the full range of chemical environments it will encounter during production molecular dynamics. The key point is this: conventional ab initio molecular dynamics simply cannot sample the thermodynamically and kinetically relevant regions of this system's configurational space. Our active learning framework can, because it adapts its training data on the fly, always adding information where it's most needed. With a framework in place, the next critical question is, how do we know it's right? Let me take you through our validation methodology. Validation is not optional. It's the scientific foundation that makes everything else credible. We use 4 independent pillars, each probing a different aspect of model quality. First, force error metrics. We compare machine learning predicted forces against DFT forces on configurations the model has never seen. A tight scatter around the diagonal with low root mean square error tells us the model is genuinely learning the DFT energy landscape, not memorizing it. Second, Bayesian uncertainty tracking. We monitor the distribution of uncertainty values throughout molecular dynamics. A narrow low distribution means the model remains confident throughout the simulation. It's not venturing outside its training domain. Third, pair correlation functions. These are the structural fingerprints of the interface. The ion-oxygen, oxygen-hydrogen, and oxygen-oxygen distance distributions. Here, we can perform diverse analyses such as radial distribution function, mean square displacement, vibration density of state, autocorrelation function, etc. We compare them between machine learning force field and DFT reference simulations. Excellent agreement here tells us the model reproduces the correct interfacial structure. Fourth, long-time energy stability. We run extended nanosecond simulations and monitor total energy drift. If there were systematic errors in the force field, they would accumulate over time. A negligible drift, less than 1/100th of an electron volt per atom, confirms the model is numerically stable and physically reliable for production use. Only after all the 4 criteria are satisfied do we proceed to production simulations. With a validated machine learning interatomic potential in hand, we can now explore chemistry that was completely inaccessible before. This is where the power of the framework becomes concrete. With our validated machine learning force field, we can now run molecular dynamics simulations that span nanoseconds and beyond, covering system sizes that include realistic hematite slabs in contact with explicit liquid water. This is simply not possible with ab initio molecular dynamics. We observe 5 categories of reactive events at the interface. Water adsorption at ion surface sites occurs rapidly and reversibly. At higher temperatures or with specific surface terminations, water undergoes dissociative adsorption. The oxygen-hydrogen bond cleaves, leaving an oxygen-hydrogen group on the surface and a proton that migrates into the water layer. The proton transfer is particularly fascinating. We observe Grotthus-type open events where protons migrate through hydrogen-bonded chains in the water layer. These processes require nanoseconds to characterize statistically. Impossible with ab initio molecular dynamics. Straightforward with our machine learning force field. Over longer time scales, we see the hydration layer dynamically restructure and gradual surface hydroxylation. The progressive buildup of oxygen-hydrogen groups on the hematite surface. These are the processes that determine how real iron oxide surfaces behave in aqueous environments, in corrosion, in catalysis, in geochemistry. But simulation alone isn't enough. We also need to understand the electronic consequences of these interfacial events. That's what the next slide addresses. The machine learning framework doesn't just generate dynamics. It enables quantitatively better electronic structure analysis. Here's why. DFT electronic structure calculations, density of states, band structures are most informative when you average over many representative configurations. But if you only run ab initio molecular dynamics, you have a tiny, poorly representative set of structures. Our machine learning force field trajectories give us thousands of diverse thermodynamically relevant configurations. From these trajectories, we select a diverse subset of snapshots, carefully chosen to represent different interfacial terminations, water coverages, and reactive intermediates, and run high-quality single-point DFT calculations on each. The results are revealing. Water adsorption causes measurable changes in the density of states. The ion 3D states broadens, the oxygen 2p density shifts, and new occupied states appear near the Fermi level. These are signatures of genuine covalent ion-oxygen interaction at the interface. Dissociated oxygen-hydrogen groups induce even more pronounced changes consistent with charge transfer from water to the oxide surface. And critically, the band gap narrows upon full hydroxylation, an effect that has direct implications for the photocatalytic activity of hematite. These results are fully consistent with density functional theory benchmarks, confirming that our machine learning accelerated framework preserves first principles physical fidelity throughout. Now let me turn to what I think is the most important aspect of this work from the perspective of this audience: transferability. This is where I want to make a crucial point for this audience. Everything we've described, the active learning loop, the Bayesian uncertainty criterion, the 4-pillar validation methodology, the long-timescale molecular dynamic workflow, the electronic structure post-processing pipeline, none of it is specific to hematite or to iron oxides. The hematite-water interface serves as the proof of concept for this study because it is a well-characterized, chemically complex, and technologically important reactive interface. However, the real contribution is the transferable computational framework rather than the specific material system. The same methodology can be readily adapted to other technologically important oxide interfaces, including titanium dioxide water for photocatalysis, zinc oxide water for photocatalysis and photoelectrochemical energy conversion, cerium dioxide water for heterogeneous catalysis, nickel 2 oxide electrolyte for electrocatalysis and energy storage, and manganese dioxide electrolyte for batteries and supercapacitors. Applying the framework to a new material system requires generating first principles reference data appropriate for that interface and retraining the machine learning interatomic potential through the same uncertainty-driven active learning workflow. The underlying computational strategy, that is combining density functional theory, active learning, machine learning interatomic potential generation, validation, and long-timescale molecular dynamics remains unchanged. This is what we mean by transferability. We are not delivering a model of hematite. We are delivering a methodology, a workflow that can be deployed across the full landscape of reactive oxide water interfaces, and more broadly, across any interface where reactive chemistry occurs at the atomic scale. From an artificial intelligence and computational methods perspective, what we've built is a physics-informed, uncertainty-aware, self-improving machine learning system for materials science, and its scope extends far beyond what I've shown you today. Let me bring this together with a summary of our key conclusions. To close, let me bring together the key messages from this presentation. We have developed and validated an active learning machine learning interatomic potential framework that bridges the fundamental timescale gap between ab initio molecular dynamics and the chemistry of reactive oxide water interfaces. The Bayesian uncertainty quantification at the heart of the active learning loop is what makes the framework self-consistent and self-improving. It never blindly extrapolates, always calling density functional theory when it needs to. Our four-pillar validation, false errors, uncertainty distributions, pair correlation functions, and long-time energy stability gives us high confidence that the trained machine learning interatomic potential is physically faithful throughout the sampled configurational space. The production simulations reveal reactive processes, adsorption, dissociation, proton transfer, surface hydroxylation that simply cannot be accessed by conventional methods, and the subsequent density functional theory electronic structure analysis quantifies the adsorption-induced electronic reconstruction in a way that is only possible because the machine learning force field gave us a rich and diverse set of relevant configurations to analyze. Looking forward, the most exciting prospect is universality. Foundation machine learning potentials trained on massive data sets spanning the periodic table are beginning to emerge. Our active learning methodology is directly compatible with these developments. Thank you. This work benefited from access to the high-performance computing facilities provided by the Irish Centre for High-End Computing, iCHEC, with financial support from the Science Foundation Ireland, National Natural Science Foundation of China, NSFC, Partnership Program with grant number 17/NSFC/5229, and the Science Foundation Ireland, US Ireland Research and Development Partnership Program with grant number 21/US/3735. I would like to express my sincere gratitude to Professor Nye English at University College Dublin for his collaboration, to Byron Rodola for valuable scientific discussions, and to Bruno Cani for technical support with the high-performance computing infrastructure. Portions of this research were conducted within the AIM2E lab, that is the Advanced Interfacial Modeling Across Energy and Matter lab. The computational results presented in this work were obtained using iCheck high-performance computing resources, complemented by additional computational resources made available through Professor Niall English at University College Dublin. The active learning machine learning interatomic potential workflow was implemented using the Vianna ab initio simulation package, and molecular visualizations were prepared using Vesta, Ovito, and VMD. In keeping with a commitment to open and reproducible computational science, supporting resources and future research updates will be available through the AIM2E Lab website and associated research repositories. Thank you very much for your attention.